Hi, I'm Ali Syed, Master of Science and Mechanical Engineering. Now I'm going to discuss briefly about air vehicle propulsion and what are the main propulsion systems we have in the market at the moment and what are the main parameters and attributes that are required to have a stable propulsion system mainly in the aircraft. Before starting with this, we'll discuss what is a propulsion, like why it is required. Propulsion is nothing but getting an external force because of some mechanical work done using machines or engines or any external force, external method by which you will get an external force which is used to get the vehicle into the motion or to move any body from one point to the other point. So the propulsion systems has been used actually anything in the car engines. If you see, whatever the power you're getting to the transmission is also known as propulsion, and in the aircrafts the energy what you use to get the exhaust through the nozzle which is used for the to move the aircraft from one place to the other place is known as the propulsion system. And in the helicopters, the whole power is what is generated on the shafts to run the whole blades of the helicopter is also a propulsion system. So basically propulsion system is nothing but getting an external force to rotate the body or move the body from one point to the other point. Whereas the propulsion system, the method, the process by which you get the whole external energy, the main energy over to the shaft or towards to the existing of a high pressure gases, it varies to which method you're getting. If it is for the two-wheeler, you're getting by the 4-stroke or 2-stroke engine, and then that has been taken in the form of tires. Whereas in the aircraft here, there are several types of engines being used with the size of the aircrafts what we use, and the propulsion systems varies with the types of the aircrafts. We'll discuss about everything briefly. Now we'll just discuss the actual air propulsion system what we use in the aircraft by taking the very common engines what we're using these days. Here, this is the basic mechanism of air propulsion system in all the jet engines and all the Airbuses, commercial cargo planes and everything you can see. Every air propulsion system which are used in the aircraft will have an intake, and then you will have a fan, and then a compressor, and the combustion chamber, and the turbine, and the exhaust duct, where you will have the mixer and as well as the nozzle. In intake duct, what happens is, intake duct is nothing but it is designed in such a way so that you can have a great mass flow rate which is projected towards the fan, so that fan will pull the whole air inside, and that will be taken by the compressor, and the compressor will compress the engine with respect to the what level of the air is required in the combustion chamber to burn the fuel in the air mixture. So to that level the compressor will compress the air, and in the combustion chamber the fuel and air mixture is burned, and that the hot gases will be exhaust towards the turbine. Turbine will increase its speed and decrease its pressure, and which will be sent with a high speed towards to the exhaust chamber, and that will be passed through the nozzle. So that is the actual mechanism what goes with the air propulsion. But the intake, how you're taking the air inside the engine and how you're doing the whole exhaust chambers and how you're getting the whole thrust varies with respect to the engines. We'll discuss that in the brief in the coming charts. Well, actually the first jet engine was actually built by the Dr. Hans Wons and Sir Frank White. These are the people who actually made the first jet engine by using the propellers actually. And before earlier that they were certain types of engines like jet engines where you don't have any propeller or the fan, or directly the whole air is injected towards the compressor which will take the engine. Now to increase the efficiency, we have to make sure the whole air is directly projected on the compressor. The compressor is getting the enough air to compress the whole air which is coming into the engine is very much required to have the greater efficiency. To have that greater efficiency, the propeller, the fan are used to drag the enough air into the engine. So we'll discuss about that inlets very soon, and here we'll discuss about working of a propulsion system. In the working of propulsion system, we'll discuss from compressor to the turbine, what is the actual cycle goes and how the inlet is being changed to the exhaust, and where exhaust is used to get the thrust in the aircraft. Where here you can see this whole process over here is explained using the gas turbine technology on the principle of Brayton cycle. Whereas as you can see, this is the compressor where the air is coming in, and that is sent to the combustion chamber with mixing with the fuel, and that is sent to the turbine, and the turbine will exit the exhaust gases, and that will give the workout on the power shaft. Whereas whatever the hot gases are which are pinching on the turbine, the energy which is getting through the turbine will be used to run the compressor. So here, this is the first stage, which is before the air is getting into the compressor, and the second stage is the stage between the compressor and before going into the combustion chamber, and the third is of the hot gases coming out of the combustion chamber and going through the turbine, and the fourth is out of the turbine through the nozzle. So we'll see these stages using the principle of the Brayton cycle, how it is working. If you just go to the graph for the pressure and the velocity, if you see from 1 to 2, which is from inlet A to the end of the compressor, you see the pressure is increasing whereas volume is decreasing. Whereas the compressor will just compress the whole air, that is the reason the pressure is increased. So we have to see to what level the pressure has to be increased so that can be mixed with the fuel and that can be used for the combustion chamber. And if you see from stage 2 to 3, the pressure is constant. That is where you are getting the energy. That is where you are getting the actual whole mass flow rate and whole mixture of the fuel in the air mixture into the engine. And where the pressure will be constant, but the temperature will increase, and also the whole velocity and the whole speed of that will increase. So again, if you see from 3 to 4, where that is from the out of the combustion chamber to the turbine, so there the pressure will drop and the speed will increase and the volume will increase. The pressure has to drop because the design of the turbine will made in such a way so that the required pressure, whatever we require at the nozzle, has to be considered with respect to the design of the turbine. So number of the blades which we use in the turbine will decide what will be the pressure of the hot gases coming at the end of the turbine. And from the 4 to the 1, which is nothing but again the pressure will be the constant. Similar way, if you see the graph for the entropy towards the temperature, from 1 to 2 the temperature will be constant from the inlet to the out of the compressor, whereas from 2 to 3 the temperature will increase a lot because that is where the whole combustion chamber, the air and fuel mixture is burnt. And from the 3 to 4, which is from the out of the combustion chamber to the turbine, again the temperature is constant, which is drop, and then from 4 to 1 its pressure is constant. So based on these principles, the whole assembly of this jet engine is done: compressor, combustion and turbine. Here, so using this process, we have seen how the fresh air which is taken through the compressor burned with fuel, and the actual workout has been, or exhaust gases with a high speed has been taken out of the engine for the propulsion system of the aircraft. So this is the actual working of the main propulsion system and on what principle it works. So now we will see the line diagram of the turbofan engine. Well, as I explained earlier, the whole assembly, the principle of the Brayton cycle has been used to put the whole assembly of each and every component of the engine, so that way from the inlet to the exhaust, at a certain point the temperature is constant, at a certain point pressure is constant, at a certain point again the pressure will drop and the temperature will increase. So on that basis, the standard assembly of a whole engine will come to this way, like the fan, or if you go for the turbo propeller engine, you will have propeller over here, or if you go for turbojet engine, you will directly have a compressor. So fan, compressor, combustor, turbine, mixer and the nozzle. So what is the actual process again goes over here? As when the whole aircraft is about to take off, or it is on the cruise time, at that period the whole aircraft will be subjected to air with certain speed. So the fan should be able to, in such a way, that should be designed in such a way that should suck the whole air into the engine chamber. That is the first one, which is air intake, that will suck by the fan or the compressor or the propeller. Fan, the turbofan engines, and the compression, the turbojet engines, and the propeller in the turbo-propeller engines. Whereas the compressor, it has a series of vanes which will increase the pressure, and the temperature will also be gradually increased. Over here, as you can see over here, there are three series of the vanes which are used in the compressor. Based on to what level you want to compress the whole air mixture, you will see how many number of vanes you require in the compressor. Whereas in the fuel burner, again the combustion process where the fuel and air mixture is ignited over here, and the combustion chamber, air is burnt along with fuel, temperature will increase and also the pressure will increase inside the engine because of the hot air gases in the instant combustion process. And the turbine, the blades will gain the energy and that will move so fast that will give an energy, that will give an external power to run the compressor which is at the front, which is after the fan, and that will also use to increase the speed of the whole hot gases which are coming out of the turbine. And the nozzle, this is the hot air will rush out of the outer diameter of the nozzle where the high pressure will increase and high speed will increase, because of which with high speed the whole aircraft will get into the motion, which is nothing but a thrust. So this is the line diagram of the turbofan engine. So the air goes, compressor will compress, combustion chamber, turbine will increase the whole speed, and this is mixture. And the mixture is a place where if you want to, few of the engines will have an extra feature of an afterburn process. If you want to do that afterburn process, that is actually being done in this mixer. So this is a mixer, and then the nozzle. This outer will dia, the whole pressure at the outer dia and the whole temperature are maintained in such a way so that the whole thrust what you are getting for the aircraft will be getting in a proper direction. So that is the line diagram of the turbine. Now we'll see what are the types of the jet engines which are available in the aerospace industry at the moment. So we'll go with the basic one. First one is the ramjet. In the ramjet you will have diffuser, burner and the nozzle. So this doesn't have any much of the compressors or turbines. This is a very simple one which will require a high speed to efficiency. This is mainly used in the missiles and the small like missiles in the supersonic jets for the military and the defense purposes, where you will have a small way for which the air to be get diffused inside, where you will have a burning process where a small ignition will be done and that will exhaust the hot gases. So if you can see, if you have seen in the videos where you can see a missile has been dropped from a very supersonic jet, you will see the smoke coming out of the missile and that is going into the right direction. So that is actually the ramjet is the process where they actually use that. And second, coming to the turbojet. In the turbojet, what happens is the intake of the air is directly sent to the pressure, sent to the compressor. The compressor is situated in the engine and that is open for the intake of the air, and whatever air is coming towards the inlet of the engine nozzle, the air will take in, and that air will be compressed, and then that is combustion process will take in, and the turbine and the mixture and the nozzle, where the compressor sucks the air required at a very high speed rotation and is required to gain efficiency. If you want to have the proper efficiency in the turbojet engine, we have to make sure the compressor is exposed to the enough mass flow rate of the air intake. That is very much required in the turbojet engines. Whereas the reason for having the turbofan and turbopropeller engines into the field is because to increase the more efficiency. The fan or the propeller, whatever we are using in these engines, will make sure the compressor is having a proper enough mass flow rate of the air so that it can run the engine with higher efficiency. So that is what happened in the turbofan. Here the fan is used to suck the air, which will increase the efficiency, and that will also decrease the fuel consumption, and that will also increase the thrust. How it is decreasing the fuel consumption? The reason because of the fuel consumption is if you are having enough mass flow rate, constant mass flow rate to the engine will work at the proper balance. The engine will work at the proper giving a constant exhaust with a constant power output. So that is very much required for engine to have a higher efficiency. So as you can see the turbofan over here, and because of the turbofan, this is inbuilt inside the nozzle structure of the engine. Some air will send to the compressor for the combustion process, and the rest of the air will be sent out of the ducts of the nozzle, which will also give the more thrust to the engine. Whereas you can see over here, like if this is the nozzle and this is the engine part, some of the air is sent over here, which is used for the combustion process, and rest of the air is sent over to the ducts of the nozzle, which will also give the thrust. With that way, if you are getting some 30 to 40% of the thrust because of air which is going to the ducts of the nozzle, the fuel consumption actually required for the aircraft to give the output thrust will be very less. So with that way, the fuel consumption will be decreased. So there are more technologies which are going on the turbofan concept at the moment to increase the more efficiency and to decrease the fuel consumption. And the second one is a turbopropeller. Here you will have a whole propeller which will be fixed to the hole at the end, at the inlet of the engine, which will be run by a propeller.
which will be, the propeller is run using a shaft which is connected to the compressor and that is connected to the turbine. So this propeller will cut the air which is coming on its way, and some amount of air is sent inside the compressor for the combustion, and the rest of the air which is going over the engine nozzle, that will give a higher thrust as well. For the turbo propeller engine aircraft propulsion systems, the majority of the thrust is gained from the air which is going over the engines, because this is made in such a way so that it has a profile drag, and which will have a very less drag, and because of the profile drag it is maintained in such a way the air which is going outside the engine will give the majority of the thrust. But the maximum thrust of the whole engine will comes when the maximum thrust will be there when the thrust what you are getting through the hot gases and the thrust what you are getting outside because of the air cutting the propeller cutting the air. If both the thrust will match, then the aircraft will get a maximum thrust. So the design has to be made in such a way that thrust what you are getting because of the hot air should also be equal to the thrust what you are getting because of the profile drag, because of the air going through the profile drag from the propeller, turbo propeller engines. So this is one of the widely used in the very huge jet planes. Like one of the, if you see the world's largest aircraft is the LS Antonov, that will have the 4 turbo propeller engines. So in that way, for the huge military aircrafts will also be using that. And then the second and the last one is a turbo shaft engine. This turbo shaft is the whole energy whatever you are getting is used to run, to get the power of the shaft which will be used to run the helicopter blades. This turbo shaft engine is generally used in the helicopters, where the whole energy will be used for the shaft, and that shaft will rotate the whole mechanism of the blades of the helicopter, which will directly cut the air and give the lift to the helicopter. So these are the types of the jet engines what we have in the aerospace industry at the moment. Now we'll see the main components of the jet engines is propeller or fan, compressor, turbine, and the nozzle. We'll see its design processes. What are the main attributes we have to consider and the parameters we have to consider for designing of each of the component, and what is its process. To start with, either propeller or the fan, we'll see it has to be in such a way that should cut the air, and the air has to push toward the backside. As you can see over here, this is the tip of the propeller fan, and this is the leading edge, this is the trailing edge, and this is the root, and this is the hub. And these days, the more the technology is going, what is happening in the technologies, they are reducing the diameter of the fan, but they are increasing the number of the blades of the fan, which is giving you more efficiency when compared to the larger wings or the larger size diameters of the fan. So in that way, these are the blades which are made in the shape of aerofoil structures in the propeller, and for the fans it is made in a constant thickness, and these are used for the propeller, these are used for the lift, whereas in the fans the design is made in such a way that the air will directly, when it cuts to the fan, when it comes out of the fan, that will impinge on the compressor. So what exactly the fan does is it will suck the air. It will suck the air and then will push the air towards the compressor. So for that thing, a helix angle, which is between the resultant relative velocity of the air and the blade rotation direction, has to be maintained in such a way so that the air what is coming hitting the fan will directly be getting pinched inside. So that are the main the things which you have to consider in the design of a propeller or the fan. To get the efficiency is calculated by using the propulsion power out with respect to the shaft powering. So by using this efficiency, by calculating the efficiency every time we design a new fan blade or a new propeller, we'll see which one is giving the more efficiency. So with that basis, we'll finalize one of the design of the design of the fan or design of the propeller, and that will be used for the required intake of the air in the engines. Well, as in the aerospace industry, the whole design of anything in the engine, like from the fan to the nozzle, everything has been done with a compromised way, because it has been done with a calculation method. It's not a proper fixed way that to get such an amount of inlet mass flow rate, the angle of the aeroplane, the angle of the fan should be in such a way, or the thickness should be in such a way. There are 3 to 4, 5 many designs are made of the fan, and everything will be tested in a such a way. Everything will be tested using the CAE softwares and CFD analysis to find out the path of the air which is cutting the blade, and whatever the design of the fan is giving the higher efficiency, that is considered in the engine. So here we have seen the design of the propeller or the fan and what are the main parameters are required. And then next part comes to this compressor. The compressor blades, if you see over here, these are in the concave shape. What happens over here is when the air goes over, when the air touches the tip of the fan of the compressor, the air will directly go down and then will come from the concave end of the blade, which will increase the pressure. This is the rotational speed and the dimension of these blades are really important to find what is the exit pressure of the air when it comes out of the compression. So what happens over here is, as we seen in the earlier design of the compressors, there are 3 to 5 vanes in the compressor. One are which are rotatory, some are stationary. So the rotatory ones, what they do is they just increase the pressure, and the stationary one will direct the air direction. And then the third one will be again the rotatory, that will increase the pressure again, and the fourth one will be the stationary, that will move the direction of the air so that exactly the air is moved into the combustion chamber. So that is the one. And the rotational blades will be in this direction as I showed in the convex, and the stationary will be in the concave. So this design has to be maintained. The variation of the air angle from the root to the tip has to be in such a way so that the air can have the proper profile drag. The air can have the air should not go away of the compressor. The angle should be in such a way that the air should circle only inside the compressor, either from the rotatory blades or to the stationary blades. The air should just move from one blade to the last blade within the compressor. That is really important in the design of the compressor. So if you just calculate the angle by doing the computational analysis or the computational analysis by using the softwares, then we can calculate what is the path of air, how the air flow is going through the blades of the compressor. So once this compressor, the air is come out of the compressor, we have the combustion chamber. Combustion chamber is nothing but like having the proper cylinders where the air fuel mixture is burned and the hot gases are come out of that. So once they come out of that, they impinges on the turbine. So turbine design is a convex design in which the velocity of the hot gases has to be increased, whereas the pressure has to be the pressure will gradually decrease. So to increase the pressure, what you do is the blades are kept in such a way. Again over here, the angle from the tip to the root is maintained in such a way, and the distance between the two blades are maintained in such a way the velocity will increase. The air angle at each and every stage is calculated in the turbine, and you see what is the velocity of the air at each and every point of the blade when the air is passing through the when the air is passing through the blades of the turbine. And using that, you finalize one air angle on the turbine and the distance between the two blades, and then the air will increase the velocity. So using that way, by trial and error method, by using the analysis in high-end softwares what we have in the aerospace industry at the moment, we can process the air flow at the different angles of the turbine, and then we can finalize the turbine which is giving our higher efficiency. So once the hot air gases come out of the turbine with a higher speed and higher velocity, that will go past into the mixer where the afterburn process will be processed, and then that will come to the nozzle. From the nozzle, as you see over here, the diameter will decrease, and the tip of the diameter, end of the diameter will be very much smaller compared to the maximum diameter of the nozzle. They are in the concave design. As the diameter at the end is less, what happens is the hot air gases, the volume is more, and that is going to a very small diameter. The hot gases will just rush out with a higher velocity. Gases going outside the nozzle with a higher velocity will make one point, but maintaining the hot gases, whatever are going out of the nozzle, has to make a proper path to get the balance in the thrust of the aeroplane. To get that, we have to calculate what will be the diameter of the nozzle in such a way, the pressure, the velocity has to be calculated for the hot gases with respect to the diameter. If the pressure of the hot gases is higher and the pressure of the atmospheric pressure around the nozzle is low, then there will be imbalance, because the whatever hot gases will come in will spread out because of the pressure. If the pressure of this hot gases is less compared to the atmospheric pressure, then what happens is you will get a very high velocity, because the whole hot gases will just impinge in one part. So we have to calculate the diameter of the nozzle in such a way that we have to maintain this constant, like same pressure of the atmospheric pressure and the pressure which is coming out of the hot gases. That has to be maintained mainly in the design of the nozzle. And we also calculate the gross thrust coefficient, which is nothing but actual thrust by the ideal thrust. And using that for each diameter, we'll calculate that and the discharge coefficient, which will help to find out the actual diameter which is giving the more efficiency. So the main things which we calculate in the design of the nozzle are throat diameter, velocity coefficient and the nozzle thrust coefficient. Once we calculate that, we can calculate the efficiency of the nozzle, which will find out, which will finally tell what is the actual thrust the aircraft engine is going to get. So in this chart we have seen the design of the propeller, the fan, compressor, turbine and the nozzle. And now we have seen the actual working of the engine, main components of the engine, and we have seen the design of the main components of the engine. Now we'll see there are many parameters and the attributes which are in the air propulsion system which we have to consider, which will be incorporated within the nozzle and which will be incorporated around the engine, and what are its interfaces with respect to this. And first one is inlets. The inlet of the nozzle has to be designed in such a way. The lip angle of the nozzle is very important one, which will decide what is the air whichever is going inside the nozzle or which is going towards the fan will have a proper profile, will have a proper profile flow. If the lip angle varies, if the lip angle is not proper, then the air which is going inside the nozzle which have separate flow, which will give an imbalance touch to the engine fans. So we have to maintain the lip angle and the design of the inlet of the nozzle in such a way so that the fan, when it is exposed to the air should be in a proper laminar flow. That is really important in this. This is designed to set the sufficient enough of mass flow rate. If you want to have a proper mass flow rate, constant mass flow rate or into the inlets of the fan, then you have to maintain the inlets of the design. Over here you can see we have also drawn a fan and the propeller. For the turbo fan engines, as the propeller won't be there, you will just have fan. So this area over here, the inlet from the lip angle to the internal part of the nozzle has to be maintained, has to be designed in such a way so that the fan gets the higher mass flow rate. In the case of the turbo propeller, where you won't have a fan over here, you will directly have a compressor. Over here, as the air will directly come in with a higher pressure, you have to maintain the design of the internal part of the engine in such a way so that the air which is coming from the propeller is cutting will have a laminar flow so that the compressor can easily drag the air. So this is a very important stuff in the inlets. This will directly vary the efficiency of the engine if that is not able to provide the proper enough mass flow rate for the compressor. So in the nozzle design for the turbofan engines, lip angle and the inside design of the nozzle is really important for that. And the second one comes to this is exhaust systems. In the exhaust systems, the exit diameter of the nozzle is maintained to get the more thrust force. As I explained earlier in the design of the nozzle, here we have to maintain this diameter of the nozzle in such a way so that we can get the enough thrust, or we can get the actual thrust which we are expecting from the engine. There are two ways of the actual nozzle. One is directly hot gases. The other one is hot gases are actually mixed with the air which is coming through the ducts of the nozzle. There are the two types, which is one is a separated nozzle and one is a shell nozzle, where you will have the hot gases are mixed with the air which is coming to the ducts of the nozzle, and in the other one, in the separated nozzle, the hot gases will have their separate path and the air which is going to the ducts of the nozzle will have a separate path. So that is the one. And the third one, you have the thrust reversers. As you can see, the thrust reversers over here at the end of the nozzle, you can see they are incorporated. They are open. Usually what happens is they just close and they will just take the shape of the nacelle. So these are used when they are open, they are removed and they will block the nacelle with nacelle outlet whichever is coming. So actually thrust reversers are used at the landing times. What happens is that will just reduce the whole friction force which are coming on the tires, or friction force which is coming on the landing gears. So that will be directly decreased by 50 to 60% by using the thrust reversers. When the plane comes with a very high speed, there has to be a proper mechanism to reduce the speed. These days, almost all the aircraft engines and all the aircraft engines are using thrust reversers. So thrust reversers will help to decrease the speed of the aircraft, will increase the efficiency of the landing gear, and they will increase the efficiency of the landing mechanism which is in the tires and the brakes mechanism. And that is mainly used or opens at the times of the landing. And then we have a fuel storage. Actually, the fuel is stored in a different places in the whole aircraft. The main fuel tank is stored in the fuselage of the airplane, from where it is directly pumped by the pressure gauge or by using the force pump that is directly transported using the pumps and the pipes into the engine nozzle. In engine nozzle, there is another tank, small tank, which will store the fuel, from where the fuel will be sent to the combustion chamber. So as you can see, the black one over here that is where the fuel is being stored, and from the main tank of the fuselage, the fuel is taken. Fuel is directly pumped to the fuel storage, and this fuel storage has to be incorporated in such a way that should not get exposed to any of the heat dissipations which come from the engine. That should not be exposed to any possible fire process. So this is kept just in between the compressor and the combustion chamber, because from the fan to the combustion it is just a cold place, and from the combustion chamber to the nozzle it is a hot area. So there is a chance, because of the hot air and a higher temperature, there is a chance of having a heat dissipation, there is a chance of having to overheat, and that can go off. For that reason, the fuel storage is arranged between the compressor and the combustion chamber. And then you have this sensing sensors. Sensors is nothing but these are used to calculate, to find out the level of the fuel in the tank, or it will just explain the status of either fuel or the heat or the temperature or the pressure or the volume or anything of which is in the whole engine chamber. These sensors will help to give the actual status of the engine running. The most common sensors which are used in the engine are electromagnetic and magnetoresistive, which will tell what is the condition of the fuel, because the fuel what is having inside the fuel tank should be maintained in a range of temperature. That should not be over 20 degrees, or that should not be less than minus 30 degrees. So that has to maintain in a range of temperature. So this sensor will give and what is the actual temperature, and that will directly alert and use an external source which will decrease the temperature or increase the temperature in the fuel tank. And then you will have the operability. Operability is nothing but the whole design of the nozzle is designed in such a way so that you can able to operate anything, or open the fan cowls or the mid body cowls or the thrust reversers open, or anything can be used, can be operable to that will give any easy access to the engine. And then you will have the installed performance. Like once you install everything from fan to the nozzle, you will install everything into the nozzle, and then you will see the whole efficiency what you are getting. You will see the whole thrust what you are getting. You should make sure you're not having any losses. When anything has been assembled from single part, 10 to 15 parts are taken, and then when they assemble into assembly, and then when you test it, mostly you will have the losses like drag, or you will have a heat losses, or you will have a energy losses. So you have to see what is the performance of the engine when it is completely assembled. That is a very important thing. For that thing, actual testing has been, manual testing is done, and also a CFD and CAE testing is also done. But once CAE and CFD testing is done to find out the major energy losses, and that can be settled down by using the incorporated, like by doing the processes. And once you have the major energy losses are taken off, and then a manual testing is done to find out to calculate each and every energy at each and every stage of the engine. So these are the actual main key parameters or key attributes what we have in the engine. And with respect to the safety measures of the whole engine or the whole aircraft, fire prevention is one of the safety measures what we have, what we need to consider. The main areas where there is a chance of having kickstart of the fire, or where there is a chance of having a blown of any engine part or blown of any pump or anything, is first one is engine nozzle or engine bay. This is also known as the fire zone. The main thing which can happen is fuel leak is often the only required failure that could lead to the fire in the engine bay. So first what we have to do is we have to take some measures so that the fuel is not leaked. We'll see what is the measures and what is the actual method we follow to prevent the fire. And the second one is a dry base. Dry base is also known as the ignition zone. It is a flammable fluid lines or refill or hydraulics or near the fuel tanks. As you can see, the fuel pumps and the hydraulic pumps for the pneumatic and hydraulic control systems are going all over the aeroplane. So in that areas also, if there is a very high temperature or high heat dissipation, there is a chance of having a fire. And the third one is the vapor space. Vapor space is nothing but the area above the liquid fuel in the tank that has to be maintained in such a temperature. Earlier, as I discussed, the temperature in the fuel tank has to be maintained in such a range. If the temperature goes off, it will increase beyond the 20 degrees, there is a chance of having a fire because of the vapor in the vapor space of the fuel tank. So these three are the main areas where there is a chance of having a fire. So actually in the aerospace industry, the three methods are used for the fire prevention. First one is prevent, alert, and the control. The prevent is nothing but controlling the fire sources. Like what they do over here is, at the time of the manufacturing, at the time of assembly or fitting the whole engine or whole fuselage of the aeroplane and everything, they will do all the measures to prevent the fire to spread. They prevent the fire to kickstart. For that, they have some preventing techniques. Like for example, they use fire arrestor. Fire arrestor is nothing but a plastic thick foam which will prevent the dry bay fires. Like as I explained over here, dry bays in the ignition zone, they will use a layer wall layers from where they will have a thick metallic plastic foam, and which will not allow the fire to spread, and that will not allow the actually fire to start, because that will have a very high heat dissipation properties. So that is used. And the other, you have a self-sealing material, the inner lines that swells and seals by itself when it is exposed to the fire. So this material is actually used in the engine nozzle, where that will also help to stop the fire, and that will directly, what it does is that will stop the fire, because that will stop the fuel to spread out, that will stop the fuel leakage. So this material is actually used in the fuel pipelines. So whenever there is a fire, that material exposed to the fire, that will do the self-sealing, and the whole fuel leakage will stop in all the pipes. So that is one preventing technique. And second one is the alert. Once the whole process of the prevent is gone and the fire has started, alert is nothing but warning, so that if necessary action can be taken to stop the fire, to stop the fire and keep the alert for the cabin crew or the passengers in the aircraft. So alerting techniques are electric resistant wire resistant as it gets heated, and the other one is the sensors. These actuators get heated and they will directly respond to the alert, and they give the property measures so that the whole cabin crew can be alerted with respect to the alarms or with respect to the announcement of the sounds. And we have the detectors. Detectors will change the wavelength of the infrared and the UV rays, because this alert, what happens is, for example, if there is a fire in the hydraulic pipeline is that you will have a hydraulic fluid in the pipeline constantly. So if there is a fire, these actuators and the sensors, by using these sensors, the whole wall of the hydraulic valve will get shut down. The hydraulic valves or the pneumatic compressed air valves or the fuel valves, they will automatically get shut off when the sensors get actuated. So by using this mechanism, the whole probability of increasing the fire can be stopped. So once this stage goes in, the final will come with the control. This is a measure to limit the fire. If the fire has already been in the plane, now you have to control that fire. You have to limit the area where the fire has been spread. For that, you have the automatic shut-offs, and you will have the fire valves and the fire extinguishers. And automatic shut-off, as I explained, in the engine area you will have a fuel pumps or the hydraulic pumps which will automatically shut off, and that can also be shut off by the pilot from the cockpit. One way that can automatically shut off by the sensors, and the second way that can automatically be shut off by the pilot because they are actuated by it. And the second one is a firewall. This is a layer between the engine and the engine wall, which will have a very high thick foam and layers, which will help for the engine to for the fire to spread out from the engine. And there are few videos, if you will see in the YouTube, if you go like testing of the Rolls-Royce engine for the fire prevention, or testing of the GE engine for the fire prevention, you can see the plastic white color foam which is around the engine. Even the engine blows out inside, you won't see any fire which is coming outside. So that is one of the firewalls which is being used around the engine. And the fire extinguishers are automatic walls which will open when they are which were powered by the sensors, or which can be actuated by the cabin crew or by the pilot. There will be a walls which will spread all over the plane and which will open, and the fire extinguisher material or gases will be blown out so that the fire can be controlled in an instant. So this is the actual one of the method in the prevention techniques which are used in the aerospace industry for the fire prevention. And then we'll see the propulsion control systems. In the propulsion control systems is nothing but controlling the whole propulsion. Like what all comes in the propulsion system? Like the engine, and you will have the tail ends, you will have the flaps, you will have the ailerons. From the engine, you will get a thrust. How is it you are changing the direction of the thrust? By controlling the flaps, or by controlling the tail end, or by controlling the ailerons and everything, you are changing the propeller, by changing the direction of the propulsion system. So for that thing, you will have a control yoke, which is an aircraft foil, and which will be used to control the ailerons. You will have the rudder pedals, which will control the rudder, and you will have the throttle controls, which will control the engine speed. At the cruise speed, the highest top of the climb, the engine has to run at its highest peak, at highest RPM. And at the landing, the speed has to go down. That can be controlled by using the throttle controls. How are these controls? How are these being controlled? Because the pilot is sitting in the front of the cockpit, and everything from the tail end to the wings and the engine has been controlled. So to control this everything, they are controlled by using hydraulic and pneumatic systems. Hydraulic and pneumatic systems are the very common technology which is being used these days in all the aircraft. Earlier in the 40s and 50s, they used to use wires and cables, and they are as mechanically powered that have a risk assessment a lot. They have to go through risk assessment, and there is a very much risk in that. So to skip that, the new technologies which have been used from the past 3 to 4 decades is hydraulic and pneumatic systems. And this, what happens is hydraulic, which is powered by a hydraulic material, which is oil and everything, and the pneumatic, which is controlled by the compressed air. So by using these systems, the movement of the flaps or the throttle control has been controlled by using the systems from the cockpit towards the engine, or from the cockpit to the tail end. What are the actual materials they use in that? The mechanical circuit, usually in the mechanical circuit, to transform the energy, to transform the work from inlet to the output, you will have hydraulic circuits which consists of rods, cables, pulleys and the chains, and of course the hydraulic pumps. And then you will have reservoirs. For the hydraulic pumps, you will have hydraulic reservoirs, oil reservoirs, filters, pipe walls and actuators. So this is a linkage of the system which actually send the direction which will increase the pressure of the oil, and because of which the whole oil will move from this point to the other point, and which will move the pulley or move the pump, which will increase the pressure, and then which will let the aileron to move up and down. So this everything is controlled by using hydraulic and pneumatic systems. Wherever you need a very accurate direction, wherever you require a very accurate movement, you use the pneumatic. Wherever you need a very instant and where you cannot take any possible risk, you will use the hydraulic systems. So main uses for that, as I explained, for the flap movement, aileron, tail end, the nozzle doors and thrust reversers. And these are also used in the nozzle to open the fan coils or thrust reversers. As a thrust reversers, and they open from the nozzle and they move towards the block the nozzle end. So these are also be controlled by hydraulic system. So this is also one of the usage of using the propulsion control system. So, and then after that we have the thermal protection. Thermal protection is a very important topic over here, because in the engine, if you see, the temperature what you're getting inside the engine of an aircraft will be very huge, will be over 1500 degrees centigrade to the 3500 degrees centigrade based on the type of the engine you're using. So with that temperature, if there is any blow on in the engine, if there is any problem in the engine, or if the temperature goes on very high, that will definitely have its effect on the walls of the engine, and that will definitely have an effect on the other side of the engine walls. So the engine walls what you are having that are thermal protected, they are protected in a such a way so that the heat, high temperature what you are having inside the engine will not have a major effect outside. Because over the outside you have a compressed air, or you have a normal air which is flowing with a very high speed. If that with that very high speed, even the temperature will increase because of the temperature inside the engine, then there are chances of having a fire. So because of that reason, the whole fire engine layer is covered by that with thermal protection, where you will have three barriers. Like this protection is used to avoid the effect due to the overheat and high temperatures in the engines. And the methods what we have is, the first one is you having thermal barrier coating for the interior surface of the perforated metal panel. So here you will have the engine, and the engine will be covered with a layer which will be into three layers. First one is a perforated metal layer, and the second one you will have perforated metallic skin of the aircraft which will have a pores inside, and the oil is sent inside that pores constantly for the cooling of the layer, to decrease the temperature which is coming out, which is exposed onto that layer. And the third one, you will have a composite perforated metallic substrate. The reason of using composite metal over here is the composite metals will have a very high melting point. So that will take a lot of time to increase its metal temperature, or to increase its metal heat. So for that reason, at the outer edge you will use the composite metallic substrate. So this is a thermal protection which is used around the engine. Similarly, there is similar of this thermal protection, or very much used with less attributes of thermal protection, is also used for the fuselage, so that should not affect any of the passengers which are sitting in the cabin. So that is one of the process which is also where the thermal protection is also required. So as I explained, the three layer methods which is used around the engine, this is commonly used in all the engines these days, as any development of the aircraft engine or the aircraft should have to follow a standard safety measures. So the most important thing which in the safety measures is also is one of this, so that the effect of one thing should not have effect on the other thing. So for that reason, thermal protection is used. And then now we'll see the fuel system. And this is the line diagram of the fuel system, how the fuel from the main tank is being sent to the combustion chamber. As you can see, this is the combustion chamber and this is the fuel tank. There are two ways. One is a gravity feed system and the other is a pressure feed system. In the gravity feed system, the levels of the fuel tank and the required the fuel where you require will directly go out through gravity. And some places you pump the fuel you require and then you will send it to the required combustion chamber. As you can see, this is the fuel pump and the valves, and the gas generator, oxidizer pump, oxidizer tank pressurization value, and the turbine, and then turbine it will go to the combustion chamber. Well, this fuel system will also be thermally protected, and this will also have a fire protection safety measures which are taken around in all the pumps. And this fuel will also have an oxidizer tank and oxidizer pump to maintain the constant temperature inside the tank. So, and then we'll see the auxiliary power units. Auxiliary power units is nothing but a mechanism which is used in the aircrafts other than engine. It will generate a power to start the aircraft engine, which will generate the power for the electricity and the pneumatic or the hydraulic controls of the aircraft. As if, for example, if you see, for the engine to have its constant efficiency, that has to run with a very high RPM. So when the aircraft is in this stable condition, the air which is coming around the fan is not sufficient enough for the aircraft, for the propeller, for the fan to run and give it to the compressor. So Alternatively, what does is these auxiliary power units will run the engine, will run the compressor, will run the turbine, and which will run the turbine in the combustion chamber, which will directly will run the compressor, and when the compressor runs with higher RPM, that will suck the whole air which is around the aircraft. So these auxiliary power units are placed at the tail end of the aeroplane, and they will use to start the engine, and I also explained they provide the electrical, hydraulic and the pneumatic. So actually the power, these auxiliary power units will run on a small gas turbine, which is not as huge as the engine, but with a small gas turbine which will have an air intake and which will have a proper nozzle which is at the end of the tail end, and it will have a oil filters, and it will also have a shaft and a generator which will take the energy which is coming out of this gas turbine, and that energy is used to start the engine, and that generator will have a gearbox mechanism from where the energy or the power which is coming to the main shaft will be distributed. So this mechanism, as you can see over here, is for the auxiliary power units, and that will also require a fuel, and it also have a fuel shut-off value and fire detector, electrical power. Here is a gearbox accessory from where the power which is coming to the main shaft will be distributed through the starter generator and also for the electrical power. Well, this auxiliary power unit which is the tail end will be capable enough to give the electricity at 115 volts at 400 hertz to run the whole electrical system in the aircraft. As you can see, when the aircraft is still about to start, there is still 1 hour left to 1 hour, 1.5 hours left for the aircraft to take off. What happens over here is, you can see still the lights are on in the aircraft, and then they are using all the mechanisms and everything in the aircraft that are actually run by the power which you are getting from the auxiliary power units in the aircraft. So, and they can provide through single or three-phase system, and they provide power to the engine staff. As we explained, as we seen the actual diagram of the auxiliary power unit, and here you can see the line diagram of the auxiliary power unit, where you will have its components as generator, start motor, fuel filter, fuel nozzle, and the bleed air manifold and the bleed air valve. So, as you can see the fuselage of the aircraft, and you can see the wing of the aircraft, and the tail end, this is where the auxiliary power unit is placed. Okay, and you can see that will also have an exhaust nozzle actually, that will have a muffler which will reduce the carbon and the most efficient gases, because they are not considered into the thrust. They won't be useful at all. So environmental effects are considered at this point over here. So these auxiliary power units are mainly divided into three main sections. So one is the power section. In the power section, you will have a gas generator portion of engine which will produce a shaft power which is required for the auxiliary power unit to run. And then you will have a load compressor section which will provide a pneumatic power for the aircraft, and inlet guide which will regulate the airflow, and the surge control valve which will maintain the stable operation of the airflow in the whole auxiliary power unit. And then you will have the gearbox section which will transfer the whole power from main shaft to in respective other shafts for the electrical or the starting of the engine, or that will be also this hydraulic and the pneumatic, which are energy, which is power which you are getting from the APU, which will be used to control the fuel control units, lubrication modules, cooling fan and the cooling engine. So here you got the diagram. This is the APU. The red lines what you see over here is the power distribution of what you are getting from the APU. So all the lines over here are, you can see from where you will have small rotors of the generators which will actually store the energy, and then from where the electric energy is taken. And over the engine over here you can see the lines from, that is how actually it passes through the wings, and that energy is also be used for the start of the engine. And here is the cockpit, it is the tail end. This is where the whole auxiliary power unit is installed. So far we have seen all the possible components and all the possible processes, all the possible parameters that are required and installed in the air vehicle propulsion system. I hope this has given a brief idea about what is a propulsion system and its history of how many types of engines and the design of the main components of that, and the main safety measures that has to be taken around. for the propulsion system, so that the whole aircraft can have a safe landing and the safe takeoff and the safe cruise speed time. Thank you.